Hey everyone. Uh, this is the promised problem solving session. We're going to look at some problems from chapter 7 and 8, all to do with work and energy. Uh, I want to say that this is mandatory watching because I will get to a problem where I need to sort of introduce an idea that I didn't mention during the lectures, and you'll see when I get there. But that problem has to do with power, and I do need to just talk about that a little bit. So I would say maybe try the problems before you watch me solve them. That might, be good practice for you. We have an exam coming up in a little over a week again, so you want to make sure you're ready for that. And I don't really want to zoom in much more on the actual picture of the problem here that I have because I want to save space to write. Right? Uh, but I can tell you, right, that this is problem number 24 from chapter 7. And so if you need to see it enlarged, maybe you can just refer to the textbook. So anyway, let's get started here. The first thing I want to do is just go through and uh, declare all the symbols that I have. Well, let me just talk about the problem first. So basically, you got the psychology textbook on a ramp essentially. There's a horizontal force applied to it with a magnitude of 20 newtons. The book has a mass of 3 kilograms and it slides a distance of half a meter up the ramp, and there's no friction. The ramp is angled at 30 degrees above the horizontal. So we want to solve for the work done. We want to solve for the network, and then. Okay, let me try that one more time. We want to solve for the work done by the applied force, by the gravitational force, and by the normal force, right? And then for the other part, it's asking us basically to solve for its speed after this has all transpired, right? So the first thing I want to do is just write out what my symbols are. And this is something I want to see you doing on your homework assignments. So we have the force, that's 20 newtons. We have the mass, that's 3 kilograms. And the distance is half a meter, right? And the only other thing I think we need is that the angle is 30 degrees. Okay, so just for the record, because I don't think I've talked about this yet, I don't really care about sig figs. But when I write my numbers out, I'll just try to use the exact same numbers that they specify in the problem statement. But I would say, in general, if you want to get a numerical answer, 2 decimal places is perfectly fine, right? Even though I would, of course, rather see you just solve it symbolically. Okay, so let's get started here. The first thing we want to do is draw the free body diagram, right? So the way that I would do this is I would draw maybe a dashed line here to indicate the surface of the ramp, right? And then I'm going to represent my mass as just a dot, right, a point. And let's draw our forces in then. So the applied force points to the right, and I'm just going to call this F. I don't feel like there's a reason to put the A there because we can get away with it essentially. And so there's that. Then we have, of course, the gravitational force pointing downward, right? And then there's going to be a normal force, and that is, of course, perpendicular to the surface of the ramp. This angle is also theta, right? Hopefully everybody can see that. And I think that's about it for our free body diagram. Off to the side, what I'm going to do is I'm going to try not to press any buttons here, what the displacement looks like, just so we have a picture of that. And it could look something like this, right? We'll call this D, the vector. And so let's first solve for the work done by the normal force. And the work done by the normal force is the easiest part of this problem because it's just 0, right? And the reason for that is the normal force, as hopefully the sketch makes clear, is perpendicular to the displacement vector, right? So we can just say that the work done by the normal force is 0, okay? So that's not so bad. We want to solve for the work done by the gravitational force, right? And I don't think we're like supposed to know this in chapter 7, but we know right now that the work done by the gravitational force is just going to be given by the well, it's going to be given by the initial and final positions of the object, essentially, right? Let's leave it at that for the time being. So what I want to do is maybe just make a quick sketch here to see how that looks. And what I could draw is something like this maybe. I'm going to make a right triangle with a hypotenuse d, and this angle here is theta, right? And so the point of this is because the delta y of the book is just given by the height of this triangle. And so using, it's going to be sine, right? Sine of theta is opposite of our hypotenuse. We would have something like sine theta equals delta y over d, right? And we can then see that delta y is just d sine theta. Now, as I've written this, it's positive, right? So we'll have to be careful when we actually use this to calculate the work done by the gravitational force, because we know, right? I was going to say expect, but we know that it should be negative because the gravitational force is pointing down, and the displacement vector definitely has a positive y component, right? And so let's write that out and see what we get. So I would say the work done by the gravitational force is going to be negative mg delta y, and this is simply negative mg d sine theta, okay? I feel like I should say that my handwriting isn't really as crappy as it probably looks here. It's just kind of hard with the tablet, just for the record. But anyway, this is the work done by the gravitational force, and maybe we could talk about this a little bit. And there's a few different ways you could show this, right? I think that maybe the clearest would be to just work with our diagram here to the left. So what I'll do is I'll just put the gravitational force here like this, right? And the way that I would think about this is I would say, well, d, the vector, right, has a component that points like this, right? If we were to break it into its x and y components, like that maybe, we could call this dy and let's say dx, okay? And those are supposed to be subscripts. It's not like a differential thing, just in case anybody was wondering about that. And so, let's see here. Okay, so if we keep going with this little diagram over here, right, what we would have is that this angle is also theta, right? And so what this means is that maybe it actually makes more sense, right, for me to draw the components of the vector d like this, and this might make it a little clearer, right? So this is dx and this is dy. And I guess I should put arrows over these if I'm being careful. And so now I think we see from this, right, that the y component of d is just d sine theta. And so what we're saying here, right, is that this just equals, let me write this out one more time. And I would never write it this way myself, but I just want to, you know, make sure that I'm explaining this as well as I can, and everybody is seeing hopefully clearly what's going on. So another way we could write this is we could write mg, right, which is the gravitational force, d sub y. Remember, d sub y is just d sine theta, and then we would have to write cosine of 180 degrees here, because that's the angle between our y component of d and the gravitational force. And so what we find is what we had written, right, which is just that the work done by the gravitational force is negative mgd sine theta. And the reason that you know, personally I was able to just sort of jump to the conclusion that it was negative mgd sine theta was because of this idea of the gravitational force being conservative, right? And the work that it does only depends on the initial and final positions of the object, right? I'm going to clear some stuff up here because I'm going to definitely need more space. So I'm going to start erasing things. If you haven't copied all this down, you know, probably pause the video and do so if you want, but I'm going to start erasing now. So let's get rid of, let's see here. Probably want to get rid of this. I feel like there should be a more efficient way of doing this, but I'm just here erasing with a pencil tip. Let's get rid of this. And then all this down here, the trig. Okay, so what we want to do now is look at how the displacement vector compares to the applied force, right? So let's do that. And I will draw that off again over here. So the displacement vector looks like this maybe, right? And the applied force looks like this, let's say. Now this angle is also theta, and we just need to essentially break f into its component that is parallel to d, and then we multiply them together, and that gives us the work done. And in this case, the work done should be positive, right, because the component of the force that we care about is parallel to the displacement vector, right? So let's see what this looks like. I could do this now for this particular part. I could say, well, this is like my f sub x, right? And this is my f sub y. Now, don't get too caught up on the fact that I'm calling it fx and fy because, right, these don't normally correspond to our normal x and y directions. What might be a better notation here is like call them f parallel and f perpendicular, right? I already wrote it. I don't want to change it, but let's just say that fx is f parallel, and then fy is f perpendicular, and you can see, I think, what I mean by that. So what we would write then is we would write cosine theta equals f parallel over f. And this tells us then that f parallel, or fx, right, just in case that wasn't clear, is simply f cosine theta. And then from this, we see that the work done by the applied force, which I'll call W sub big F, is going to be F d cosine theta. And I don't have to put another trig term in here, right? I don't have to write cosine of anything now. Well, if I did, let me do that because maybe that would help. If I wanted to, what I would write is cosine of 0 degrees, right? But in practice, I would never do this because that's just 1. And remember that the work is like I shouldn't say it's a dot product, and so we can just sort of throw away the component of the applied force that's perpendicular to the displacement vector, right? And so this, of course, is just 1. And so we have now calculated all the individual works, right? And so at this point, I will probably have to start erasing things again. Let me see here. But we see, right, that the total work done on this thing, or the net work done on this thing, really is just given by the work done by the gravitational force and the work done by the applied force, right? And so let me erase the diagram then at this point. I think that's what I'll do. All this stuff on the left here, because I would like to refer to the things that we found for the different parts of the work. So erase, erase, erase. Oh, I didn't mean to erase that. I'll rewrite it, because that's kind of something we need to know. Yeah, I want to get rid of this too. Okay. Apologize that this is time consuming here. So what I wanted to rewrite before I do anything else is that this here was, remember, the work done by the applied force. Okay. So now we can write out our network. And that's just going to be, I want to write FD cosine theta, and then I'm going to write minus mgd sine theta. Okay? And then remember, right, from the work energy theorem, that this equals the change in kinetic energy. Okay? And I guess I'm going to have to erase again because I need more space. So let me get rid of this stuff here on the right-hand side now. I think we have everything we need to take this to completion. And all we're going to do then is just write out what the change in kinetic energy is explicitly, right? That's it. So get rid of all that, and what we find is, well, first of all, it says in the problem statement that the book had 0 kinetic energy at the start of the displacement, right? So remember that delta K is simply K final minus K initial, right? But this is just 0. So delta K is the final kinetic energy of the book, like that, right? And so putting this all together, what we find is what would be almost our answer. I'm not going to do the algebra, but you can definitely ask me if you have any questions about how you would go about this. I think hopefully everybody knows, though, is I would say, one more time, invoking the work energy theorem, right? FD cosine theta minus mg d sine theta equals 1/2 m v squared. And at this point, it's just a math problem, right? We would just have to solve for v. We would just write v equals whatever it is. I mean, you just multiply both sides by 2, divide both sides by m, and then take the square root, and you got it. Okay, and I thought that this was a good example because here we have a non-conservative force that is actually going to give our object some kinetic energy, right? As opposed to take it away. Because we're used to, hopefully, or maybe not yet, but I think we'll probably get pretty used to the idea of looking at friction and things like drag or air resistance being our non-conservative forces, and those will, tend to reduce the kinetic energy of an object. But we see here that there's no reason a non-conservative force can't increase the kinetic energy of an object. And remember that this term on the right, it just has to be positive numerically, right? Even if I don't evaluate the numbers, because the mass is positive and v squared, right? The square root of any number is going to be positive. Well, any real number. Okay, so that's that. Hopefully this helped a little bit. If you have any questions, of course, feel free to reach out one way or another, and I will get you straightened out. So I'm going to just clear everything here, and we'll move on to the next problem. So I think I have to zoom back out. There we go. Okay. This is, and I can make this a bit bigger. This is Chapter 8, Problem 113, right? And we're going to start again. Well, I'll read it. So a 30-gram bullet moving, well, I guess that should say at a horizontal velocity, right? A 30-gram bullet moving at a horizontal velocity of 500 meters per second comes to a stop 12 centimeters within a solid wall. What is the change in the bullet's mechanical energy, and what is the magnitude of the average force from the wall stopping it, right? And so we're going to start by writing out what we have. And so mass of the bullet, and this is where we need to convert units, right? And this is something I haven't really talked about because it's also something I don't find terribly interesting or important, because you can literally just ask the internet to do this for you. But just so you see what it looks like, right? If I want to convert this, I need the conversion factor. So 30 grams, and I know that 1,000 grams is equal to a kilogram, right? So I have to multiply this number by 1 essentially. So something like this: 1 kilogram, right, equals 10 to the third grams. And notice, right, that that the grams, right, these units cancel, and we find that this should be, I'm really bad at powers of 10, but we need to move the decimal place 3 spaces to the left, right? So it should be, and I guess check me on this because like I said, I'm bad at powers of 10, but it should be, it's going to be 2 zeros. Wow, this is embarrassing. Hang on. No, it should just be 1 0. Okay, let me fix that. And this is why you just ask the internet, okay? I mean, in case you didn't believe me, right? So this should be 0.03 kilograms. So move the decimal place 1, 2, 3 to the left, right? Okay. Cool. And then we have a velocity that we don't need to change, right? The velocity is just given in what we need, which is meters per second. And then for the, I'll call this D, right? This is 12 centimeters, and we need to convert this again, and I'll do this one more time. And a centimeter, right, is 1/100th of a meter, or another way of saying this is that 1 meter contains 100 centimeters, right? So these centimeters cancel, and we divide 12 by 100, and we should find that this is 0.12 meters, okay? And I think that's all we have to do as far as converting units goes. Again, this is not something I find terribly important, or I consider terribly important, or find interesting, but it is something I'm supposed to, I guess, at least mention. So that's how you do this. Okay, anyway, with that, all that, nonsense out of the way, let's actually solve the problem here. And I'm going to clear this and just rewrite it because you know I need space, right? So Let's just quickly rewrite this. The mass of the bullet was 0.03 kilograms. The velocity, and I'll call this the initial velocity actually, I think that makes sense. It's 500 meters per second. And then d, the stopping distance, was 0.12 meters, okay? And so this is going to be, well, it's a combination again of work and energy, right? And so first, for the part A, I don't think this is so bad, right? Because we have that the initial kinetic energy is 1/2 mv initial squared. And the final kinetic energy is simply 0 because it comes to a stop, right? And if you wanted to look at what, say, the initial and final gravitational potential energies would be, we can do that because I did mention this, and I think it might be good for you to see that this is just MGH, right? And this is also MGH because what we're imagining happens is, and this is perhaps an approximation, right, but probably not a bad one, is that the bullet, right, it basically just moves in a straight horizontal line. And this is because it has such a large x component of velocity that probably the change in like the y position is pretty much negligible, right? So, but if you wanted to write it, you could, and you would see that, for instance, like E naught, right, is just going to be 1/2 m v naught squared plus mgh. And another reason I think it's safe to assume this is because we're not told anything about the y position, essentially, right? And E final is just going to be 0 plus mgh. And so if we were to take the difference, which is what we're being asked to do, right, we want to solve for delta E, which of course is E final minus E initial. What we find is that the mgh terms go away, right, because we're going to just subtract E naught from E. And all we're left with after we do this is negative 1/2 m v naught squared, right? And that's the answer here. It's just negative 1/2 m v naught squared, whatever number that works out to be. So I'm going to go ahead and erase this. Actually, you know what? I'm just going to clear this all because I think we have, it's probably fine. Okay, so let me just rewrite what we found for A, right? We found that delta E was negative 1/2 m v naught squared. Cool. So now it's just realizing that the force that is exerted by the wall on the bullet, right, is what is going to bring it to a stop. And what we would have here, because I think it's probably a good idea to make a sketch, is we would have something like the bullet's displacement points to the right, and then the force of the wall points to the left. And we don't really know the nature of the force from the wall, right? I think it's probably safe to say it's something like friction because, you know, as the bullet bores itself into whatever material the wall is made of, there will be friction between the bullet and the wall material, right? But we don't really know much more about it except for it's just the thing that makes it come to a stop. And that's fine. And they ask for average force because it seems like maybe the force might not be constant. But again, we wouldn't even really have any way of knowing. So here, let's look at what we have. Well, let's write it like this maybe. we're going to say the work done by the wall equals, and we have to probably write F with a bar over it just to indicate that it's negative. Or, sorry, the average. I'm getting ahead of myself here. To indicate it that it's an average force, right? And the distance it's acted over is d, right? And then we have to put in cosine of 180 degrees, which of course makes this work out to be negative F sub W d, right? And then it's just a matter of equating the work done by the wall, which is really the only thing doing work in this example, to the change in kinetic energy, right? And we find when we do that, that we wind up with something like this. And this really is just the work energy theorem, right? This is just saying the net work done on the object is equal to its change in kinetic energy. And so we can clean this up, right? We can get rid of the negative signs, and actually I'll just go ahead and do the algebra here because it's not bad really at all. What we're going to find is that this works out to be m v naught squared over 2d, right? And that's the force that the wall exerts on the bullet, the average force. And so I as I'm thinking about this, I don't know that I can really justify why we're using an average force here. So what I want to say is this, right? This is not really anything I have to write down, but just a little discussion conceptually, is that even if the force is varying, right? Like say it's increasing or decreasing, what we would have to do if it was varying, right, is an integral. But we're okay here because we're actually just asked to solve for the average force, right? And so we don't need to really do any fancy math because I think if we did, well, we really couldn't, right? We would have no way of even doing, say, like an integral here or something to calculate for the work. And then also, just for your information, right, this is not a huge deal. It's not something that's super important for our purposes, but you know, there is definitely a relationship between say the average value of a function and a certain way of calculating the integral of that function over some interval, right? And that's all we really need to know here. I don't think that, you know, it's super important to stress, but that's kind of what's going on. Yeah, you know what? I will just write this down just because I'm pretty confident I can remember it, right? And so, and this is just for your information. Like, you could probably fast forward this and it's okay, but just in case anybody wants to know why this is what we're doing here. And there's an idea from integral calculus, right, that the average value of a function over some interval, right? Let's say it's the interval between a and b, is simply given by 1 over b minus a times the integral from a to b of f of x with respect to x, right? And so what we would do is we would like kind of just pattern match this to what we just did, right? And so we could say something like, well, let's think of this, and remember I drew the bar over this to indicate that it's the average value. Let's identify this with the force of the wall, and let's identify b minus a, which is just the length of the interval for the integral here, with d, right? And so if we rearrange this, what we would find is f bar x b minus a equals the integral from a to b f of x dx. I think it's very dangerous that I'm trying to teach you math, but you know, that's what we find ourselves doing, or I find myself doing, I guess. And so if we rewrite this, then what we could do, or if we just make an analogy to what we just did, we have something like this: the force of the wall, d, and then this equals, say, like changing our limits of integration here. Say the force depends on position, right? It's just this, and this is work on the right hand side, right? This expression is definitely the work done by a force over an interval of length d, a one-dimensional force. Okay, and that's it. I'm gonna stop now because I shouldn't be doing math. It's dangerous. So let me clear this. We'll move on to the next example I have here. Now, why won't you go? Okay, so I have to, I guess, just go the other way. Okay, let's look at this one because this is this has to do with the idea of power, right? And I can definitely zoom in a little bit here. Oh, not that much. But this is problem number 99 from chapter 8. And this is where I have to talk about power a little bit. I have to just give you an idea of what it is. So I'm just going to say that power is defined to be, let's say it's work applied or work done over a time interval, right? And that's really all we need to know here. And power is going to have units, in case you're curious, right? Of, well, the units of work are just joules, and the units of time are just second roots, right? So this is just a joule per second, which is also called a watt. And I think I can actually derive this for you if we just think about like a one-dimensional force doing work on an object, right? So I'm going to do that really quickly, this idea here. Well, actually, I'm sorry. There is a formula that we need related to power that I'm going to derive. If we all just accept that it is work done over a time interval. And hopefully there's nothing, you know, outlandish about that because it's just a definition. But what I want to do is I want to write out something like just the definition of work, right? In one dimension, work can be thought of as something, we can write it like this maybe. Okay? And what we can do is we can just divide both sides of this by delta t. Right? And what we find is that, well, we already just stated that power is the time rate of work, so we can rewrite this simply as P. And then here, we can rewrite this as f sub x. And thinking back to kinematics, right, what is delta x over delta t? It's just v, right? And so we can write this, I should say v sub x if I want to be, I guess, careful here, but I'm going to drop the subscripts now and I'm just going to write something like this. I'm going to write that P average, right, then is going to be given by F V average. And this is a result that we're going to need in this problem, which is why I'm deriving it, and also talking about power in general, right? So power is just the time rate of work. And, you know, you can also think of this as just energy, right, over a time, because work and energy are for all intents and purposes, the same thing, right? They have the same dimensions, and so hopefully we're all comfortable with that idea right now. So you might see that power is also defined to be something like delta E over delta T. And that's a perfectly fine way of also writing this. Okay, let's solve this though, and I don't think this should take terribly long. Yeah. Okay, so I want to set a good example and do this. So the average speed of this swimmer is 0.22 meters per second, right? And the average drag force, I'll just call this little f, is 110 newtons. And that's all we're really given, right? So this is going to involve, well, let me read this problem first. I realize I didn't do that. So this is problem number 99 from chapter 8, right? In case you can't see the tiny text. And what it says is a swimmer moves through the water at an average speed of 0.22 meters per second. The average drag force is 110 newtons. What average power is required of the swimmer, right? So we're going to make two diagrams here. We're going to draw the free body diagram of the swimmer. And what we must have is, let's start with the stuff that doesn't matter. You're going to have a gravitational force, right? But to counteract that, right, we're going to have a buoyant force. And this is something we don't need to worry about, at least for right now, because this is like a fluid mechanics idea. And all we're going to say is that let's just trust that the buoyant force cancels out the gravitational force, right? So the force that the water exerts on the swimmer cancels out the gravitational force, so the swimmer can swim at a constant height above the bottom of the pool without, doing anything really to counteract the gravitational force. So what we're going to have, though, on the swimmer is we're going to have a drag force, though, right? And this is assuming that the swimmer is moving to the right. And then there's going to be a force that this is tricky. I'm not sure how I want to word this, but I was going to say something like a force that the swimmer needs to exert on himself. But that kind of doesn't work, right? I think we all remember the guy trying to lift himself up with the buckets. But we know that there has to be some kind of a force on the swimmer. And this is a bit tricky. You know what? I don't even really know that much about swimming, but let's just say that swimming is really just moving your body in such a way that the water exerts a force on you, okay? Let's leave it at that. So we're not, by doing this problem, we're not, breaking any of our fundamental assumptions, right? And that would be like a complicated thing to discuss in depth. But just, let's just say that what swimming is, right, is just moving your body in such a way that the water exerts a force on you to propel you forward, okay? Hopefully everybody's all right with that. And if anybody is like an expert swimmer and wants to explain this to me in more detail, I'd be interested in hearing. But so anyway, the net work, right, over on the swimmer, let's say, this makes me uneasy because remember that work is a scalar, so we wouldn't typically write it with a component, but I'm going to do that. And note that we're thinking about our usual XY directions here. This is just to indicate the X here, right? Again, remember work is still a scalar, so it wouldn't have an X component, but this is just to show that we're thinking about the work done by the forces that are in the X direction or the negative X direction, okay? Is going to be over some, let's say over some time interval, right, is going to be simply big F minus little f times whatever displacement the swimmer has for that time interval, right? You can probably see where I'm going with this. Oh, wait a second, though. No, I think this is fine. Okay. So, yeah. So what we do is we just divide both sides by delta t, right? So we say w sub x over delta t equals f minus little f times delta x over delta t, right? And if we identify the left-hand side here with the average power and the right-hand side here with this force and then v bar, right? And remember, we're able to say that it's the average velocity because we're thinking about the average power, right? So a discussion of the average power in this situation implies a discussion of the average velocity. And all we need to do then is I might have messed this up. I think I messed it up. I apologize for that. Let me try to fix this as quickly as I can. And I'm so far into this, I'm like almost an hour, that I really don't want to stop recording and start again. So, my bad. What I want to do is I just want to say something like this. I want to say for the swimmer to move at constant speed, right, constant speed, implies that the acceleration is 0, right? And so then what this means essentially is that the force that the water is exerting on the swimmer has to just equal the drag force, right? And so while the swimmer is not exerting a force on himself per se, right? If you think back to our discussion, he is certainly expending energy to, say, apply a force to the water that therefore applies a force back on him, right? And so we can just identify the average power in this case to be the force that he applies, or she applies, I guess, or they apply, doesn't really matter, times the average velocity. And so I don't know why I'm just imagining Michael Phelps, okay? That's all there is to that. And so this simply works out to be 110 newtons times 0.22 excuse me, meters per second, right? And that's it. I'm dying. And so you can calculate the number here and just see what it is, and that's the power that the swimmer has to supply, right? It's just the energy that the swimmer expends over some arbitrary time interval. I realize this was a little bumpy. Hopefully everybody's okay with this, and if you have any questions, of course, excuse me, feel free to reach out. But I think that this is actually the way we were supposed to do this. Okay. Let me clear this, and we will do the last example here, and we can conclude. So let me see which why is it doing this? There we go. So this is the last one that we want to do, and it looks probably like it's kind of involved, but it's really not that bad actually. Okay, so this is chapter 8, number 22. And a 60 kilogram skier starts from rest at a height big H equals 20 meters above the end of a ski jump and leaves the ramp at an angle theta equals 28 degrees. Neglect the effects of air resistance and assume the ramp is frictionless. What is the maximum height H of his jump above the end of the ramp? If he increased his weight by putting on a backpack, would H then be greater, less, or the same? And so this is just going to be conservation of energy, right? Now that I'm looking at this, I think it's also going to be trickier than I thought. Okay, let's just do this though. So writing down what we have, mass 60 kilograms. Big H is 20 meters. Theta is 28 degrees. And, well, I wrote a comma, so let's just put that mu is 0, right? Because it's frictionless. Okay. So what we want to do is look at the initial energy, right? And so what I'm going to say is that I'm going to use a subscript of 0 to indicate this, a subscript of 1 to indicate this, and a subscript of 2 to indicate this, right? So 0 subscript means he's at the top of the first hill. 1 subscript means he's at the top of that little bump, and then 2 subscript means he's at his maximum height. So let's do this. So the initial mechanical energy, right, is just going to be gravitational if we define our y equals 0 to be here. And I think that's a sensible choice. So what we would write here is just that this is mg big H. Then at 1, he's going to have some kinetic energy, right? We'll call this 1/2 m v1 squared. Then at 2, he's going to have some kinetic energy plus some gravitational potential energy, right? Like that. So what I think we want to do here is use some knowledge from kinematics, because we would have, like, you can go through and try this without doing what I'm about to do, and you'll probably find that you have too many unknowns to actually solve for anything, right? And so what I want to talk about really quickly is that at 2, right, the velocity vector is going to be, let's just say, v2x and 0, right? Because he's at the maximum height, and so the y component of velocity is 0. And so how, then might we work around this issue, you might be wondering, and the way is kinematics. And what we want to do is to note that at 1, right, there's a velocity vector that perhaps looks like this. And we can think about kinematics now and realize that the x component of this velocity vector stays the same, right? And what that means is that this simply equals v1 cosine theta, and then this is still 0, right? And so now we're good, because what we see is when we have a vector that only has one component and we square it, it just works out to be that, I'll write this out, but like v2 squared, right, if you were to apply the Pythagorean theorem, would just work out to be v1 squared cosine squared of theta, right, like that. And so we need to solve for v1, right? The speed or the magnitude of that vector. And we do this by equating E0 to E1. We find mg big H equals 1/2 m v1 squared. We can cancel the masses, and we find that v1 squared, I'm not even going to take the square root because we want it squared, right, is simply 2g big H, like that. So what we can do is, I'm going to get rid of this stuff on the bottom here. Maybe I'll leave the V2 thing there because we should remember that. And now what we find is substituting in, basically taking this here, is that okay, so we're going to equate E1 and E2 now. Okay, and so making the substitution, we find 1/2 m, well, we found v1 squared to just be 2g big H, right? And then we found that v sub 2 squared is just v sub 1 squared cosine squared theta, which means, let's write this out and be careful here. For the kinetic energy, we're going to have this 1/2 m, and then v1, nope. So v1 squared is 2gh, right? So this is 2g big H, I should say. So this becomes 2g big H cosine squared of theta, and then plus mgh. Now, what we'll find when we go through, and I'm going to get rid of, I'm just going to maybe write this one more time, and get rid of this thing down here, is like we can probably see that the masses will just go away, right? Because there's a mass common to each term in this equation that we've written. Remember that this right here, right, is the very bottom equation is just E1 equals E2. And so we can get rid of that. Interestingly enough, we can actually get rid of G as well, right? Which is kind of strange, but cool. And so if we clean this up, I'm kind of rushing now, so double check my algebra here. But the approach here is good. This is what we wanted to do. On the left, this just simplifies to big H, right? And here we have the 2's going away, and we find that this just works out to be H cosine squared of theta plus little h, right? And we don't have to do much work to solve for little h, so let's just do that. We find that it's going to work out to be big H times 1 minus cosine squared of theta, like that, right? Upon simplifying it. And this, let's see here. Well, cosine squared of theta should be bound between 0 and 1, right? So this looks like maybe we just calculate the number here. I'll do that. Because we want a sanity check here, right? We want to make sure that that little h is not larger than big H, I think is what we really expect to find here. So let me just do this really quickly. So I'm going to say 20 times 1 minus cosine of 28 degrees squared, and tell me what that number is. Okay, so I'm finding it's 4.4. Let's say it's about 4.41 meters. And so we found this interesting thing where the mass canceled out, right? And so we find our final answer has no dependence on mass, and indeed it doesn't even have any dependence on the gravitational acceleration, right? And so the answer to part B is that nothing really would change, right, if his weight was increased, or if we can equivalently if his mass was increased, right? And so the answer looks like it should be no. Okay, and that's it for this problem solving session. We did 4 problems. I know that the swimmer one was a little bit bumpy. Hopefully everybody is okay with what happened there. I will maybe do one more of these before the exam for whatever topic it is that we're doing next. I want to say that it's going to be momentum, linear momentum. And so hopefully you found this helpful, and I can continue to do maybe one of these like a week approximately for the rest of the term. Okay, I will see you in the next video.